Yeah, so brain architectures or biological systems have very interesting concepts that we don't use today in computer architectures. This is the result of millions of years of evolution trying to optimize power and energy, so which is precisely what we are trying to do right now in computer architectures in the IoT space. So what we had to learn from this type of biological systems is that how our brain and our nervous system in general is able to really do three things much better than what we do today. The first one is selectively choosing which information needs to be treated and why. So this is something that today, when we do data acquisition with IoT devices, we never really think about that. We try to take always the worst case scenario, we collect all the data, and there is actually a lot of energy, a lot of information that is collected, which in the end is not going to be used. And today there's not even enough space to even collect all this information, so the storage. So we need to learn how to change that, and the main idea to go behind this concept in brain systems is really events. So when you have particular events that you know because of the application or the particular thing you're sensing that are relevant, this is when you actually do the acquisition. So this is one of the main aspects, and it will really benefit a lot for reducing the energy on the analog front end and the acquisition part from the IoT devices and on the computer architectures as well. The same thing goes on the part of the processing. When you think about processing, in general, you process the data with general purpose processors. These general purpose processors are able to run very often any kind of algorithm, with a more or less efficient way, but in general they are general purpose. So one of the main aspects here is that anything that you see in biological systems, and particularly in the nervous system, they are highly specialized and adapted to whatever particular organ or signal you are sensing. So in this case, the idea is to create extremely heterogeneous architectures, very specialized, and selectively activate the computing blocks that you really need or that are required at the particular moment or kernels that you're going to run. And this will actually save pretty much almost 2 orders of magnitude on energy efficiency with respect to what you have today. And the last final part that we have in the brain, which is very unique, is the fact that you don't have a separate storage system for data and compute inside. So everything is integrated in a 3-dimensional structure where you have the data close to what you're going to process. And this is where it comes the part of edge computing, so really where you sense the data, and the second aspect of in-memory computing, which is essentially the idea that you don't have to change information between the memory subsystem and the processing, but you actually are going to treat the data directly in the memory. So that's why we have created an accelerator that is called Blade, which computes on the bit-line logic. So it's a bit-line logic accelerator for edge devices. And this is actually the idea that you treat the data with simple operations directly where you are actually storing the data. Yeah, so an extra element that is important in this new computer architecture is you want to make the things as open as extensible for the large community to be able to work on. So this is the idea of creating a community that works on these concepts. So instead of just doing like classical vendors like ARM or Intel, where they actually share with you maybe the instruction set, but you don't have the full system to understand the vulnerabilities or how to improve it, what we are doing is all these elements that we are creating, both Blade, our coarse-grained accelerator for in-memory computing, as the processors we do, all of them are relying on open hardware, so RISC-V, instruction sets that actually can be used by anybody, and everything is released as open source hardware.